Time? Yeah, great. So I'll do an introduction. It's a bit longer than usual, and it will become clear of being needed. So it's a pleasure to welcome Professor Soumik Pal to the statistics seminar. Soumik is the Robert Warwick Professor of Mathematics with dual appointment in applied math and statistics. Soumik has been a leader in probability theory across campus, and also the leader of a not so secret, but also not so secret organization called the Counter-Robotics Initiative, promoting this new area that has ramifications all across mathematical areas, but also computing areas, which allows to revisit many concepts and in probability theory, statistics, and extend them. I will say a few words about Soumik's approach to probability theory. So the way I was trained in probability statistics, students would say, I want to do probability statistics, and people would say, well, why don't you do functional analysis first? And then you say, okay, now can I do probability statistics? You say, not so fast. You need to do integration first. And then you say, okay, can I finally do probability statistics? Well, you do measure theory first. Right? And you say, well, can I do statistics now? And you say, but conditional expectation has a projection in Hilbert space. Go back to linear operator theory, right? And for me, like probability theory and statistics has been this way, but through collaborations with Soumik, I rediscovered the joy of probability theory as it always should have been, right? Remember that probability theory was born when Pascal, the philosopher, and the Chevalier de Marais, a nobleman, both obsessed with gambling and instinct to God, changed everything. And solve puzzles together and have a lot of fun. So working with Soumik is going back to those sunny afternoons in your youth, where you were playing cards and throwing dice and trying to understand that. And so with Soumik, when you research in probability theory, it's like, I would say, oh, let's do this, for many samples, and you say, oh no, actually, let's start with a simple case. Let's have fun with that. And so Soumik's vision of probability theory is one that starts with fun, and then introduces measure theory and functionalities and all that only when it's necessary. Right? And I also want to take this opportunity to do a round of applause for Soumik. He was just elected as a fellow of the Institute of Mathematical Statistics. And I guess the proof that he was on that.
Thank you very much, Zai. Thank you very much for this very kind introduction. So I don't know if you're aware of this, but Chris Birdsey here is certainly aware of this, that the West Coast probabilists are sometimes called the West Coast group of coin tossers. This is to distinguish our philosophy of doing probability for otherworldly groups, that we start with probability by taking a coin and tossing it and rediscovering everything from starting from coin tosses. So I'm very proud of learning probability that way, and I hope to continue to do probability theory that way by coin tossing. So today I'm going to talk about, as I was saying, this new in some way, this beautiful area that has suddenly transformed many of our research areas. This is the area of optimal transport. Some of you may have heard about this, some of you may have heard about bits and pieces about it. So I want to give a general overview, because sometimes it's very hard to get into new people because you don't know what people know and what people don't know. If you ask me questions, please stop and ask me questions, and I'm happy to answer any question now. It looks like it's big and vast, but it's still, most of the stuff is actually unknown. So let me start with the basic problem here, which is, how do I go to the next slide? Okay, here we go. Okay, the first problem of optimal transport starts around 1781. If you remember 1789, that's like the French Revolution. So shortly before that, the person who introduced this is this gentleman called Gaspard Monge. This photo is actually taken by me 2 years ago. There is this beautiful, beautiful cemetery at the edge of Paris called Cimetière du Père-Lachaise. If you go there, you will find the cemeteries of many of the French luminaries, including Edith Piaf, for example, but also Gaspard Monge. He has this bust there. His body is actually not there. It's in Pantheon because he's considered one of the French greats. But this old bust is actually still there. You can visit it. He posed the following question, which I have translated into the modern framework. This is not exactly what he posed, but similar. I have two probability distributions, mu and nu, on my Euclidean space Rd. Now, I want to find a map T that takes Rd to Rd such that if x is sampled from mu, then Tx has a distribution nu. And then among all such probability distributions, I want to find the expected minimum squared error between the two. Okay, so Monge was an engineer and a military general, and he really had a practical problem in mind. The problem was something like this. Suppose you have a mold of sand, and you have a ditch which I have drawn in an inverted way, and you need to carry grains of sand from the mold to the ditch, ensuring that the entire column over a certain area is transported to an entire column there. What is the most efficient way of doing this? Okay. So in modern language, he did not actually have the square. He was only looking into the Euclidean distance. But in modern language is this: among all t, which are maps from Rd to Rd, which push forwards mu to nu, what's the one that is closest to the diagonal? That's the kind of question we're asking. You'll immediately see that the problem is difficult because there may not be even one single such t. Here is an example. If mu is my delta mass at 0, so unit mass at 0, and my nu is Bernoulli, like half-half, -1 and +1, there is no t which will take the delta mass at 0 and split the mass. This is just not possible. So not only this problem is ill-posed, it may not even have a solution, not even a single candidate. Okay. So for a long time, people were stuck. It seems like an interesting problem, but we don't know how to do anything about it until our next breakthrough comes from economics. Leonid Kantorovich, the famous economist and mathematician. This is a pattern in optimal transport theory. The breakthroughs come in waves, and they come from different parts of science. It tells a very compelling story about ideas of scientific ideas. So Kantorovich, what he does is that he tries to relax Monge's problem. And what he does is the following. I have two probability measures, mu and nu, which are probability measures on Rd. Kantorovich says, look at the set of couplings of mu and nu. Now, if you are coming from statistics or probability background, you have some idea of couplings that you have heard of. Throw away those notions. Those are not important. What is coupling is any joint distribution whose one marginal is mu, the other marginal is nu. So if you have two distributions, let's say normal 0, 1 and normal 0, 1, a coupling is any joint distribution whose first marginal is normal 0, 1 and its second marginal is normal 0, 1. There are infinitely many such couplings. In fact, there is always one, which is the product, the independent coupling of two normal distributions. That's always there. So this set is non-empty, the set of couplings of mu and nu. And if there is a map which takes your mu to nu, then this very degenerate object, which is x comma t of x, that's a coupling. Because x is coming from mu, and t of x by definition is coming from nu, and therefore that's a coupling. So Kantorovich reformulated Monge's problem in the following way, that instead of looking into the infimum over maps, look into the infimum over couplings, the expectation over the coupling of y minus x norm square. So instead of looking for what map is there, such that I'm closest to the diagonal, spread out your mass. Look into the space of, in some sense, doubly stochastic matrices, such that your deviation is as close as possible to the diagonal. It's Kantorovitch's formulation. Why this is a very striking and useful thing, but you have to understand that era that which Kantorovich was working, this was when linear programming was coming into view. Danzig and Kantorovich, and they were all doing this linear programming, which is this idea of solving linear problems over convex sets. And they were easy because one can write codes to solve it. Well, what birth of early computers. This is actually a linear problem over a convex set. What is a convex set? It's a set of couplings. If I have a joint distribution whose marginal is mu and nu, another joint distribution is marginal in mu and nu, convex combinations also have marginals mu and nu. This function, as a function of this measure gamma, it's a linear. Expectation is a linear. This problem is actually minimize a linear function of a measure over a convex set of measures, probability measures. And therefore, it's a linear programming problem. And so very easily, one can show that there exists always an optimal coupling. We don't know if it's of the map or not, but there will always exist an optimal coupling. Now, the next question is, how does this optimal coupling actually look like? If I have a normal distribution and a gamma distribution, and I try to align them optimally, using their deviation by square deviation, how does it look like? The answer, actually, we had to wait for another 50 years to Jan Brunier's remarkable theorem. So Brunier proved the following theorem. Imagine that your measure mu has a density. Nu does not have to have a density. Imagine that the mu has a density. Then the optimal coupling is always of the type of that Monge was looking for. So remember what was Monge looking for? Monge was looking for a function t that will take r to rd such that mu will be pushed forward to nu. And this is the best one. Kantorovich look at all couplings. Now Brunier in the 1980s proved that solve Kantorovich's problem, the optimal solution that you get is also of the type of Monge. And not just that, here is a real kicker, which is that the Monge's map, the optimal map, must be the gradient of a convex function. And that's unique. So again, let me repeat, it's a remarkably strong theorem, and it has several parts. I want to have mu and nu. Mu has a density. I want to find a coupling which is optimally coupled. There will exist a convex function whose gradient of the convex function, which is mapping rd to rd, will push forward mu to nu. That's the unique solution of Kantorovich's problem. That's the unique solution of Monge's problem. And so the optimal coupling is actually degenerate. It lies on the gradient of a convex function. With this one single stroke, Brunier links the problem of Kantorovich's problem or Monge's problem to an underlying geometry. Why convex function? If I want to transform our standard normal to a gamma distribution, my Jan Brunier's theorem, there would exist a convex function whose gradient will push forward normal to gamma and is the optimal one. Why would it be convex? Why is this the unique thing? These are all the mysteries you learn by actually studying the proof. That optimal transport is a very geometric subject. It somehow lifts the underlying geometry to probabilities. Why is there suddenly a lot of interest in optimal transport? If you recall, like I think it's the last NeurIPS, which was in December in Vancouver, one of the plenary talks was one optimal transport and Schrödinger bridges. It's everywhere. If you search online, every day you go to arXiv, there are tons of papers that are coming up in statistics, machine learning, AI, mathematics. Why? Well, actually, even when Kantorovich wrote his own treatise, he has this striking statement in the beginning of his book. Soon after this work began, it became clear that the methods being developed there could find a far larger field of application. He was really referring to, his relaxation and his economics application and so on. But of course, he had no idea how much application actually lies in the future, which we are seeing now. So I'll come to some of these applications. This is a slide I've taken from J.C. Hütter's of different applications that are being used for optimal transport these days. So I'll say a little bit about why. One of the reasons why people like optimal transport is that they want to compare two distributions, and they want to compare two distributions in a way that is somehow better than Kullback-Leibler. which is my favorite divergence. So an optimal transport is more robust than Kullback-Leibler. So here is an example. Take uniform 2 to 3 and uniform 0 to 1. The Kullback-Leibler is, of course, infinity because they don't share the same support. But the optimal transport distance is actually 2. It's like basically you take 0 to 1 and you shift it by 2 to make it 2 to 3. And that's actually the optimal transport distance. So this is one case that you see that even if the supports are disjoint, the Wasserstein 2 metric, which is this optimal transport metric, which you may have heard this word, is always finite. It's 2. What Kullback-Leibler may not give any answer. So this is a particular use that is used in manifold learning here. I want to talk a little bit about this one, regression with uncoupled data. This is a rather interesting example where you have kind of a time series, but not quite where you can track a particle. An example of this is single-cell genomics. So imagine you're studying the cell development. So cells are being developed. Now you want to pick a cell and you want to open it to see its characteristic. When you open the cell, you're killing it. So at every step of the cell development, you must pick different sets of cells, destroy them, take the observation, let the rest of them develop further, and then look at them, and so on and so forth. So it's a different thing. So it's like a time series of cell development, but it's not the same cell that you're tagging over time. They're different groups of cells. However, if you want to compare between these populations of cells between different time points, you need a way to match them. And you want to match them in a way which is optimal. And that's the way that you use optimal transport in doing this business. So this brings me to matching problems. Matching problems are ubiquitous in economics, for example. So optimal transport plays a big role in matching. Computer vision and graphics. Okay, so there again, if you search by optimal transport and computer vision, there are beautiful graphics that you'll find on Google Images of people. So for example, take an elephant and you want to optimally bend the image to make it a donkey. How would you do it? There's a ready-made algorithm that you can go from optimal transport, which will do this. Sampling and image generations, these are very, very big topics, and like, for example, in generative AI, a lot of generative AI actually uses optimal transport-based methods. So I'll come to this bit later. Any problem, essentially, which has some underlying geometry. So optimal transport works very well if you want your data analysis to preserve the underlying geometry. And there's a reason for this. If you have two delta masses, delta at a point X and delta at a point Y, and if you compute the Wasserstein 2 distance between them, it's just the Euclidean distance between X and Y. So for delta masses, you get the Euclidean distance, and you raise it to the data distance by optimally matching. So that's the reason. Early on, people realized that there is a big problem with optimal transport, which is that they're expensive to compute. And I'll come to this point. That's where my entropy regularization is coming. But I do want to promote this new book on statistical optimal transport by Chewy, Ninesweed, and Rigole. And it has a quite up-to-date account of the statistical developments. But up-to-date is getting old by every month. I mean, new things are coming up so quickly, it's hard to keep track of that. Okay, good. So what did we learn? We learned that optimal transport makes sense. It's a very good object. People will use it because they want to do something with data and geometry, but it is expensive to compute. So how do we bypass this bottleneck of computation? And this is where the idea of entropy comes into play. So as we say that Monge's solutions, they are highly degenerate, they are supported on a graph. This is my Brunier's theorem, which says that the optimal map are supported on the gradient of a convex function. We want this. We really like this fact because it captures the geometry of the space. But we also don't like it because it's brittle. Anything that is supported on a gradient cannot be estimated perfectly with the data and is expensive to compute because it's brittle, it's non-robust. So to rectify these problems, we introduce entropy, which is an old concept. So it's a measure of degeneracy. So if I have a probability measure nu, which has a density f, my entropy of nu is the integral of fx log fx dx. It's infinity if it doesn't have a density. So if you're familiar with Shannon's notion of entropy, that's a negative of this one, but optimum transport always uses this sign convention. An easy way to remember is that if you look into the entropy of normal with mean zero and variance sigma square, it is negative log sigma. So what does it mean? It means that when your normal distribution becomes more degenerate, sigma goes to zero, your entropy goes to infinity. And when normal distribution becomes more flat, when sigma goes to infinity, then your entropy goes to minus infinity. So that's the thing you should remember. That entropy is capturing the measure of degeneracy in the sense it becomes larger and larger as your measure becomes supported on a smaller and smaller set, in some sense. Related to entropy is the notion of Kullback-Leibler or relative entropy. So Kullback-Leibler of two measures P and R is, of course, you have seen this. This is log dp dr dp. Now, several people over the decades have introduced the following regularization of optimal transport. Filmer, the economists Galichon and Salanier, but it really took off when Marco Couturi, who's currently in Google, but then he was in Apple, he suggested this following in the machine learning literature. Look into this object again. This is my set of couplings of mu and nu. So all joint distributions with one marginal mu, the other marginal nu. Okay, so that's my convex set. In my optimal transport problem, this integral. Now what I do is that I pick a positive epsilon and I write it at this plus epsilon times entropy of gamma, and you minimize this object. Okay. So I want to explain to you what is happening. If epsilon is 0, this is my Monge-Kantorovich solution. I know its solution is given by Brennier's map, which is this, the one which is supported on the gradient of a map. This is degenerate. This doesn't have a density with respect to Lebesgue measure. For every positive epsilon, however, that map is inadmissible. Why? Because if epsilon is positive, such a solution will have infinite entropy, and this will not be in the infima. So every time you take a positive epsilon and you solve this problem, what you're getting is an optimal coupling, which is not degenerate, actually has a joint density. And this joint density, this solution is called the Schrödinger bridge at temperature epsilon. So this is a picture. Again, I think this is, I've stolen from this book of Marco Couturi and Gabriel Terre, which is that what is happening with increasing epsilon, that this solution, the Schrödinger bridge, tries to stay along the gradient of the convex function, but then it diffuses. As epsilon grows, it becomes more and more diffuse. As epsilon goes to 0, it becomes more and more degenerate. Okay, that's the idea of the Schrödinger bridge. I'll come to why this solves many of our problems, but let's try to understand what this new object is. So I want to explain that this, if you look into this new object, now this is a convex problem because entropy is a convex function, the well-known convex function. This is linear, and I'm trying to minimize over a convex set. So this actually always, because it's a strongly convex function over a convex set, it has a unique solution. How does this unique solution look like? Again, we kind of know and we kind of don't know. And so this is how it looks like. There's a theorem which actually comes from statistics literature, Forte, which is in 1940s, and Ruschendorf and Thomson, they were all actually doing statistics back then. If you know this vein of the literature, which is trying to find joint distributions with given marginals, that's the kind of thing that they were doing there back then. And so they actually had figured out the solution back then, which is that the Schrödinger bridge at temperature epsilon must have the following density. The density with respect to the product measure, mu and nu, will have two components. The first component would be exponential of the cost function over 2 epsilon. That's always this Gaussian kernel that comes into here. And the second part cannot be jointly dependent on x and y. It must be separable in x and y. Okay, so it must have this solution. These potentials are called Schrödinger potentials, and they're actually unique up to a constant. Just like in the Brownius function, we don't know what the convex function is. We know it's a gradient of a convex function. We don't know what the convex function is. Similarly, we don't quite know what these potentials are. We just, which was, this is mu and that is mu. So that's a typo here, mu and we just that they must satisfy the marginal constraint that the joint distributed density has to integrate to mu and nu. There is exactly one. And if you find that one, that's your optimal solution. Yeah. Okay, so this is the product. So this is, so mu times nu is like mu x, nu y, the product density. Right, so gamma is a joint density, gamma epsilon is a joint density of xy. Mu, the product density mu x, nu y is a joint density of xy. And so it's a Radon-Nikodym derivative of the two. Good. I will explain to you how you can solve this, but this is actually easy to compute from data. Okay, might not look like I made some progress, but we have. It's actually easy to compute from data, and that's why the statisticians were actually doing it in the very beginning, and I'll come to that. Why? But when you get such a joint density, again, people are not happy. People are never happy. They always want more and more. So we wanted to estimate the Monge's map. Very hard to compute. I will show you. This one is actually fairly easy to compute. But what this gives you is a joint density and not a map. And so what people will do is that they will convert it into a map. How? By taking conditional expectation. So given x, you take the conditional expectation of y given x under the Schrödinger bridge, and that gives you a map. This map is not going to be a Monge's map. If you take x under this map, you're not going to get nu, but it will be close. That's the idea here. Good. How do you actually, yeah, sorry. Oh, this is a bad name. This is because I'm following these papers by Jonathan Nilsweet and others who call this barycentric, but by now they have changed their mind and they call this entropic Brownian potential. This field is full of these names which nobody really understands why, but they have been just following. It's a bad name, but it's just barycentric here just means taking average conditional expectations. Okay, good. How do I solve for my Schrödinger bridge? And this is actually, you may have heard about this, the famous algorithm Synchron, but statisticians have been doing this for decades. They call it IPFP, which is iterated proportional fitting procedure method. So the credit should have gone to them, except that nobody knows outside of statistics what IPFP means. So that's a lesson for you guys. If you're going to name something, name it cool. So the proof of Forte, which actually shows this theorem here, that must look like this, actually is a beautiful proof which actually uses the IPFP algorithm. And I'll tell you what this algorithm is. Take epsilon to be 1 and take mu and nu to be uniform over 2 points. So x is my 0, 1 and y is 0, -1. Okay, so I'm trying to match two uniform distributions that were supported over 2 points. I will first create a matrix which is like the type e to the power minus x minus y norm square. And if I plug these values, this will give me e to the power -0, e to the power -1/2, -1/2, e to the power -2. The matrix are positive numbers. Now I want to fit marginals uniform on both sides. So I want to have these sums should be 50/50. Those sums should be 50/50. How do I do it? Let's try to make the row sums 50/50. I will calculate the row sums and then divide by the row sum, multiply by 1/2 to get 50/50. Easy. Now I've messed up my columns. Now I'll calculate the column sums, divide by the column sums, multiply by 1/2. Now I've fixed the column sums are 50/50, row sums are messed up. So we iterate back and forth between the two. And you go on doing this. Well, there's a theorem that says ultimately you will reach a matrix which have the right marginals. And that is also your Schrödinger bridge. Okay, remarkable. But it's such a simple algorithm, actually gives you the answer. And so solving optimal transport, if you want to solve the actual optimal transport on finite original linear programming problem. This is quite computationally complex. And so by using the synchronous, it becomes an order to get your complexity from n cubed to n square by doing your synchronous algorithm. Of course, it only works as long as you're positive. Positive, but small. Epsilon equals to 0, you're back to optimal transport. There's nothing you can do about it. A lot of recent work actually has been focused on trying rates of the synchron algorithm. The matrix algorithm by linear algebra, it is known to converge exponentially fast under some assumptions. And this is an old and famous theorem of Birkhoff. And that actually uses this very original metric called Hilbert metric. You may have heard about it. It's a beautiful concept which proves exponential convergence for the finite datum. For a long time, statisticians actually knew that the problem is very non-trivial when you're trying to have two densities and you're trying to do IPFP for densities, or it's a very non-trivial problem. A lot of recent probability literature in optimal transport actually tries to answer this question. So I have written down a few of these results, which are only in the last couple of years, and then most of them will give a result in convergence rate, which is of this type that under appropriate tail assumptions, your algorithm is converging geometrically fast in the iteration step n, but the constants depend on epsilon. And these constants blow up very badly as epsilon goes to 0, which is my main point of interest. Okay, and so it's kind of okay. I understand when epsilon is moderately large, it's exponentially fast. But then what happens when I take epsilon going to 0? And typically what people do is that they will take epsilon to be like of the order of 1 over log n for size n data. So they're kind of going to 0 slowly with the data size. We don't know. Except this particular paper, Chiarini et al. In 24, they actually do something uniformly for small epsilon, but our understanding is pretty badly. And there's a reason why this is so difficult for small values of epsilon. And so in a paper of mine recently, we actually show that this low temperature behavior, this is not temperature, but temperature behavior, is because that these iterations of synchron, they are like what is sometimes called a gradient flow of Kullback-Leibler in a very distorted geometry, and the geometry has singularities. And if you reach one of the singularities, you can get slowed down. And there's a picture here, geometric picture here, why it is difficult to analyze. And that's in a recent paper of mine. Okay, what else do we know? Well, as I said, people are interested in computing optimal transport. People can't because it's expensive. So they put a little bit of epsilon positive and they compute Schrödinger bridges. But are they doing a good job? Is computing the Schrödinger bridge giving me my optimal transport result as my temperature goes to 0? Fortunately, the answer is yes. And so this discussion actually started with a beautiful paper by Mick who used control theory to prove that if you compute your entropy-regularized cost, which is this cost, then as epsilon goes to 0, under rather weak conditions, it converges to your Wasserstein 2 cost. So if you're just interested in computing the distance between your data and the model in the Wasserstein 2 sense, you're not making that much of a mistake by computing it for small epsilon. They are converging. This reason is because of a theory of probability called large deviations. And in fact, if you look into the Schrödinger bridge, which is the optimal coupling for this problem, that also weakly converges to the Brunier map, which is the map that you actually want to estimate. So again, you're not doing a terrible. But as I said, people are never happy. They want to understand, good, it's converging, but at what rate? And so that also is actually known in a paper of mine, and then shortly afterwards in Conforti and Tamamini, we show that this rate of convergence, that if you compute this object here, and if you look into the difference between this from the optimal transport cost over and divide by epsilon, then this is the entropy of the two measures, mu and nu. Now, I want you to appreciate here something, that this rate, which is this minus, this doesn't depend on the actual coupling. It only depends on the marginals, mu and nu. So as long as you know what is the entropy of mu, as long as you know what is the entropy of nu, you can estimate how far you are from the optimal coupling. Because remember, we are trying to figure out what is the optimal coupling. If it enters into the error rate, then it's something is bad. But this, fortunately, doesn't happen here. We also know what is the epsilon squared term, and unfortunately, our luck runs out because that does depend on the optimal coupling. Because I'm a probabilist, I want to bring in Brownian motion. Why is it called the Schrödinger bridge? Why is this solution of the entropy-regularized optimal transport called the Schrödinger bridge? That's because this is a solution of a problem that Erwin Schrödinger posed in 1931 and 32 in two of his papers. It's a very natural problem, which I will try to explain to you. Take a box, let's say the unit cube, or even this room, so it's a cubic room. Now, take gas molecules, and suppose the gas molecules, take it in a balloon, put it at that corner of the room, and then you prick the balloon. What will happen? The gas will start diffusing. Now, at what rate will the gas diffuse? The temperature of the room. Suppose the temperature of the room is very low, close to absolute zero, then the gas will diffuse very slowly. Now, suppose at time 1, even when the temperature is very low, you see that the gas molecules have all come up into this area of the room. So something very unusual has happened. The temperature is very low, gas molecules are not supposed to move, and yet we see some rare event where the gas spread from that corner of the room to this corner of the room. The question that Schrödinger asked is, what path did the individual gas molecules take? Is that clear? Well, the gas molecules has all the path in the room. It could like go from here, go to that corner, go to that corner and come. But somehow your intuition says that should not happen. If the gas molecules don't want to move, the temperature is very low, and yet we see all of them moving from here to there, they should move in such a way so that some kind of kinetic energy is minimized. That makes sense. Why would they waste energy roaming around the room when it costs them so much energy? So they should somehow minimize the kinetic energy and move along as efficiently as possible. It was proved in Hans Filmer that the efficient in this movement is exactly what the Schrödinger bridge will dictate. So what does that mean? It means that you have the molecules there, you have the molecules there. These are two probability distributions. Suppose the temperature is epsilon. Solve the Schrödinger bridge problem between these two. That gives you some joint density. Sample from the joint density and move each of these almost like a straight line from there to there. And that's what the Schrödinger bridge will do. It automatically minimizes the kinetic energy. So I want to show a movie here. This is taken from Lenaik Shiza. Okay, so what are we seeing here? Ignore the first part of it. Oh, God. Ignore the first part of it. What are we seeing here? These red points are going to the blue points. So the red points are my initial configuration of my these gas particles. Blue points are my terminal configuration of my gas particles. And they're going from one to the other. So I have three pictures here. Epsilon equals to 0. Epsilon is small and epsilon is large. And what this is showing is the solution of the Schrödinger's problem is what paths do these gas molecules take. When epsilon equals to 0, the red and blue are perfectly matched by optimal transport. Once you have matched them, the molecules move straight line from wherever it starts to wherever it ends. And that's what we are seeing here. For small values of epsilon, you see that the red and the blue points, they are matched according to Schrödinger bridge. And how are they moving in between? Like a Brownian bridge. If you give me the initial position and if you give me the terminal position, they're moving like Brownian bridge with temperature epsilon in between. So very small fluctuations, almost a straight line. Over here, same picture, but epsilon is large. And now Brownian bridge is free. It says Brownian bridge has no force to make it like a straight line. And so it just moves like Brownian motion in some sense in the beginning. And that's exactly what we are seeing here in these pictures. You see straight line, almost straight line, and really no constraint. Okay, good. So a very, very short review of statistical issues here. So these are some of the main theorems that people have done. So suppose I want to estimate my optimal transport using empirical data, and I want to compare the actual optimal transport. Or suppose I want to figure out the entropy regularized optimal transport for empirical data, and I want to compare with actual entropy regularized optimal transport between two densities. And so people have figured out what are the rates of these objects are. So if you want to actually estimate optimal transport distance from data, you suffer from the curse of dimensionality. Your rate is n to the power minus 2 over d, where d is the underlying dimension, which makes it hard to estimate. Imagine if d is 40, you're not really making any progress. On the other hand, there's a remarkable paper of Mena and Nalsweed, which shows that for any positive epsilon, if you want to estimate the entropy regularized optimal transport, you're always in the parametric rate of n to the power minus 100. There is some assumptions on the tail behavior, they're sub-Gaussian, but otherwise this is true. Remarkable. Of course, nothing in life is free. There is some cost that you're paying. It's this cost epsilon. And this cost epsilon also comes up in this order here. There's a constant depending on epsilon, which blows up pretty badly, super exponentially. But if your epsilon is fixed, parametric rate. What about central limit theorem? You can't have central limit theorem for this one because the bias seems to be bigger than the variance. You can't really have central limit theorem, but you do have limit theorem for this guy, proved by a paper of Gonzalez-Sanz, Lubis, and Nalsweed. The central limit theorem actually was predicted by a paper of mine with Zaid and our student Lang Liu. And what we consider is a variant of this problem, where slight variant of the entropy regularized problem, where it could explicitly calculate all the central limit theorems. And we kind of made the claim that this must be the same for the actual one, and this indeed turns out to be true. Okay, good. So in the final part of this talk, I want to talk about joint work with Medha Agarwal, who is here, Zaid is here, and my student Garrett Malkahi, who is currently enjoying Paris. So the story starts from transformers. There are these two papers I want to refer to. Okay, the transformers, the idea came from Vaswani et al. Really, what we are following is this paper of Sander et al. In 22. I also want to talk about a little bit in the et al. Okay, this slide is just there to introduce here. You can ignore it for the rest of the talk. What I want you to understand is that if you have a transformer, what you're doing is a sequence of iterations where every iteration is some kind of linear transformation. And you go from iteration to iteration to iteration to iteration. That's what you're trying to do. The problem that I'm going to show you is a mathematical problem. And the mathematical problem arose from this paper of these guys. And they were trying to understand transformers. So what is the math problem? The math problem starts with an iterations of Schrödinger bridges. So let me explain what do I mean by iteration of Schrödinger bridges. Start with the density rho naught. For the density rho naught, for a temperature epsilon, consider a Schrödinger bridge with both marginals being rho naught and rho naught. Now, this might look very peculiar to you. I'm trying to do optimal transport between rho naught and itself. This is a trivial problem. If I'm trying to optimally match with rho naught to rho naught, the optimal map is just identity, right? No problem with that. So why in the world would I worry about Schrödinger bridge? Well, forget about that. I'll come to that. The thing that you should remember is that the Schrödinger bridge is never going to be the identity. Why? Because as I said, Schrödinger bridge always admits a joint density. And so identity is out of the question. It will always have some joint density between the two measures, rho naught and rho. Now, from that joint density, look into this barycentric projection, and that gives you a map, which is B0 of x, which is where will I land on average if I start from x? My temperature epsilon is very small. At epsilon equals to 0, 50 is my Brunier map, so I will be exactly at x. If temperature is small, as I said, Schrödinger bridge approximates my Brunier map, and so I'll be close to x, but not exactly x. And so I'll have some kind of what you do is that you look into twice the identity minus the barycenter, and you push forward your rho naught, this should be rho naught, to get your rho 1. Okay, so this requires a bit of an explanation. My barycenter is approximately identity. So twice identity minus the barycenter is twice identity minus identity, which is again approximately identity. So I am looking into a sample from rho naught, and I'm approximately moving it by identity, and I'm getting a sample of rho 1. So rho 1 is not very different from rho naught, slightly different. But that slight difference is what is important for us, as we will see. Is this clear? So that gives me, my rho 1. So if x naught is rho naught, then x1 is the distribution of twice x naught minus this barycenter of x naught. That gives me rho 1. Now I iterate this. As I said, we did not come up with this scheme. This was in the Sanders et al. Procedure. So just bear with me what we are doing. Something quite fun is happening. And now what you do is that you iterate this. At every step, rho k, compute the Schrödinger bridge between rho k and rho k. Again, this is approximately an identity, but not quite. And now what you do is that you compute the barycenter for this Schrödinger bridge, and then you push forward your rho k by twice identity minus vk to get rho k plus 1. Okay. So again, rho k plus 1 and rho k are very close. So I have rho 0, rho 1 is very close to rho 0, rho 2 is very close to rho 1, rho 3 is very close to rho 2. So there's a tiny amount of changes happening at every step, but this change can accumulate over time. And the question we're asking is what is happening to the sequence as I look into longer and longer set sequence of iterations, and my epsilon is going to 0. This is a picture. This is my rho 0, which is some kind of bivariate data. This is actually done over data. This is not actually done over densities. This is done over data. At every step, I find my barycenter using my synchron algorithm. I do my push forward of particles, and I go on proceeding this. So what I'm doing here now is that I'm scaling my time by epsilon itself. So now, because everything is moving very small for every small epsilon, so I can put larger and larger of them in a small time interval. And so I'm basically scaling time by in orders in magnitudes of epsilon, and I'm looking into this sequence. And it looks like epsilon goes to 0. These histograms are evolving continuously. Right? Once you see this evolving continuously, you can ask, does it solve a PDE? And the answer is yes, it solves a PDE. Does anybody want to make a guess? Well, not obviously my collaborators, but anybody wants to make a guess what this PDE is. Where is the sequence converging? What do you see here? The heat equation, very good. You clearly see that there is a smoothing here going on. This picture looks very much like normal distribution. There's a smoothing going on here, and that's because what we show here is that this converges to the heat flow. Okay. Out of nowhere, we get this flow, the heat equation coming here. And this actually is not our observation. This is the observation that we picked from their paper in the analysis of transformers. We just isolate it from their paper, and we try to understand this phenomenon. Okay, why would this happen? Why would such a bizarre iterations over the set of probability measures give us a nice solution in the end, which is the heat flow? So a little bit I want to say here. Well, this comes to, again, how close is the Schrödinger bridge to the Brunier map? So I said that the Schrödinger bridge is very close to Brunier map, but the question is how close? And what we show in the paper is that if you look into the barycentric projection under the Schrödinger bridge for a nice density of the second coordinate given the first, well, that's the identity. Of course, that's the leading order term. The next order term is actually 1/2 epsilon, the score function of rho. The score function is this gradient of the log rho. So that's the one that comes up here. So this correction is this 1/2 of gradient of log rho. Why? Again, I'll come to this why, but this is the deviation from the identity. And now the mystery is somewhat understood. If you look into twice x minus the barycenter, then if you just put equality here, this becomes x minus 1/2 gradient of log rho. And so what my iterated Schrödinger bridge system is doing is trying to discretize a particle system that is following this way. That the k plus 1th point is kth point minus epsilon over 2 gradient of log rho k xk. If you have never seen this kind of particle system, these are called forward Euler iterations of an ODE. There is something called forward and backward Euler iterations to run ODEs. This is a forward Euler iteration of the ODE. And if you replace this difference by the derivative and solve for it, you'll get back the heat. And that's the reason why you expect these iterations to converge the heat. So in the last 1 minute, I've run out of time, but last 1 minute, I just want to say why this equality actually holds here. It's because what we show in the paper is the following, that if you look into the same marginal Schrödinger bridge, if you take the same density rho and look into the same marginal Schrödinger bridge with temperature epsilon, that's a joint density. That joint density is actually very close to the joint density of the stationary Langevin diffusion taken at time point f0 and epsilon. So there's a joint density that you get from the stationary Langevin diffusion. That joint density and the Schrödinger bridge joint density are very close. And once you observe that, the rest is actually coming from which gives us the score function. Okay, so that's all I have to say about this. I just want to repeat a little bit. I just want to say, end it here. Forget about these things. It shows something quite interesting here. One is that there is a way to estimate the score function using Schrödinger bridges. And people, including some of the people in Axel Munk's group, are actually exploring the statistics. We don't fully understand, but this gives you an idea. So the idea is that if you look, the score function, as you know, is notoriously difficult to estimate from data because you have discrete data, you're trying to estimate gradient of the log of the density. You can try to smooth it by kernels and then try to estimate it. It's very difficult. But it shows here that it might be possible to estimate it by using the synchron algorithm. Why? Because if you take the same set of data, you can run your synchron algorithm and estimate your barycentric projection. And what I have proved here, barycentric projection minus the identity map is epsilon times the score function. And so if you can estimate the barycentric projection and subtract of this identity map, then you're getting an estimate of the score function. And so under some restricted assumptions, this has already been proved to give you the estimate of score function or the entropy. And people, I know several groups are actually working very hard to get better statistical estimates of this. I think I'll end here, and thank you for your attention.
At the very end, you mentioned that we can use this kind of optimal transfer way to estimate the score, but in that case, we also need to choose epsilon.
Right.
And I guess at the very beginning, you said like there are some cases we can choose epsilon to 1 over log n to actually try to mitigate those exponential effects. But in that case, like when we estimate score function, we probably have to use a different epsilon. And the question is how we can choose.
Very good. So you see already you have an open problem in statistics, which is that figure out a way of choosing epsilon depending on n such that if you take epsilon n, you get your, take n IID data points, you get your Schrödinger bridge by computing from there, plug in your estimate epsilon n, and then you show consistency. You show that the deviation of the barycentric projection minus identity divided by epsilon n converges to the score function. Perfect, that's already an open problem. This must be true. And as I said, some initial bounds is there. They have figured out, this is Gilles Martin, for example, is a person who has done some work on this, but it is far from over. It's actually widely, in some sense, yeah, wide open from completion. It's an open problem.
So explain what the Schrödinger is using the volume and gas release and so on. Is it somewhat related or a special case of the least action principle?
It is related to the least action principle. So there is, okay, there's a dynamic version of optimal transport, which I really haven't gone into. But instead of saying that, okay, I'm going to match one point here to one point there, one can say that look into all paths that connects this point to that point and try to minimize some function of this path. A natural function of this path is kinetic energy, which is look at the velocity of the path and I trying to minimize the integral of the norm square of the velocity of this. If you minimize this, you get optimal transport, you get Bernoulli's map. Instead of having kinetic energy, if you take kinetic energy and you integrate the Fisher information as well, then you get this one. So epsilon's time Fisher information will give you the Schrödinger bridge. So it is indeed a least action principle where the action involves kinetic energy and Fisher information. Fisher information appears everywhere in this whole